Assalamualaikum warahmatullahi wabarakatuh. This is the third part of a tutorial for chapter 6. Okay, let's go to the problem 674 here. From a work production perspective, which one is more valuable? A, thermal energy reservoirs at 675K and 325K. So we can say that in this condition, this will be the source and this will be the sink. And for B, the source is 625K and the sink is 275. You can see between the two, A has higher source, 675, higher temperature compared to B, while the sink, A has higher also, of course, or in other words, B has lower sink compared to A. So let's try to first make sense of this. Okay, you know that for heat engine, we have source. Okay, in this case, we are given the TH and the heat from the source will be supplied to the heat engine. So we have heat engine there and work net will be produced from the heat engine out to the out from the heat engine, and the remaining will be thrown out as the image to the sink. So we have sink here, and sink we are given STL. So in this case, then to compare between the two, we just look at the ideal condition then, which one will have a better possible performance, okay? Or maximum performance in that case when we are talking about the reversible. So if you look at the oops, okay. All right, let me just continue the performance. The thermal efficiency for reversible, you know that the equation is nothing but 1 minus TL over TH. Okay, so basically we will just be using this equation to compare between the two. So for the first part, the condition, okay, basically the thermal efficiency for reversible condition here would be TL 3 to 5 Kelvin divided by 675 Kelvin. So if you calculate this, you will get 0.519 or 51.9%. Okay, that will be the ideal or the reversible performance, 51.9% efficiency. What about B? So we can do the same. 1 minus the TL is 275 Kelvin divided by TH is 625 Kelvin. So if you do this, then the answer will be 0.560 or 56% or 56.0%. All right. So comparing the two, you can see that B, okay, has more valuable or more potential to produce more what we call that work compared to A. So therefore B is more valuable. Okay, so that is the first problem, 674. Let's move to the next problem. Okay, 681. Heat engine receive heat from a heat source at 1200 degrees Celsius. So you have the heat source at 1200 degrees Celsius, and you are given the efficiency 40%. The heat engine does maximum work. Okay, let's just highlight maximum work. We'll get to that later, and that will be 500 kilojoule. Okay, determine the heat supplied to the heat engine by the heat source. heat supplied to the heat engine by the heat source. So we know that this is QH. Okay. The unit is on kilojoule. So yeah, it is. We are not talking about the rate. We are just talking about the amount. Okay. So QH, heat rejected to the heat sink. You would expect that that would be QL, and the temperature of the heat sink. So we know that this will be TL. Okay. Let's go to next page so that we can solve this proper. Okay, so let's draw the diagram to describe this condition. You are given the source, the temperature of the source. So you have TH equals to 1200 degrees Celsius. So that is our source. And from there, then we are supplying QH to our heat engine. And the heat engine has an efficiency or thermal efficiency of 40%. Okay. And with that, then it is producing work of 500 kilojoule. Okay. Let me just write here, W net. Well, it's not dot. Eraser. Okay. Okay. And of course, not to violate the Kelvin Planck. So the remaining QL will be thrown to the sink, and we are not given the TL. The sink has a temperature of TL, which we will need to find out. So I believe pretty much this describes our situation. Okay, so how to find the QH? We are given already efficiency, we are given TH, and we are given also W net. So having efficiency then and also W net, we can find QH. If you remember, for A, you can relate in terms of the efficiency, thermal efficiency of a heat engine, which is nothing but W net divided by QH. Okay, the amount of work produced divided by the amount of energy supplied to the heat engine. Okay, so if we rearrange this, of course, we know the efficiency, we know the work net, we will need to find the QH. So QH is nothing but W net divided by the efficiency, thermal efficiency. So plugging in, you have 500 kilojoule divided by the efficiency is 0.40. Okay, calculating this, you will get 1250 kilojoule. Okay, so that will be the QH, the amount of heat supplied to the heat engine. All right. B, heat rejected to the sink. Well, we can now, since we have QH, we have also W net from the problem. To find QL, we know that we can just simply use the energy balance. Okay, energy balance relation. You know that QH is equals to energy coming in equals to energy going out, which is QL plus W net. Okay, so we know QH and we know W net, so we can find QL, which is nothing but QH minus W net, which is QH just calculated 1250 kilojoule minus W net is 500 kilojoule. Okay, so if you calculate that, you will get 750 kilojoule. Okay, so that would be the heat rejected to the heat sink. All right. Last one, in order to relate the temperature, then we know that we will need to relate with the reversible condition. Okay. But then this is where we have this maximum work. Okay. If we take this maximum work as what related to the ideal situation, in other words, we can say that this is the ideal or the maximum amount of work possible from this heat engine, and that will be only be possible for reversible process. So if you take maximum work as a reversible process, so that would be the most that this heat engine can perform, then we can relate between the system. Okay, so the efficiency, as what we defined before, is actually nothing but the efficiency of a reversible process. And therefore, we know that for reversible, you can also relate simply by the temperature between the two reservoirs. Okay, TL, 1 minus TL over TH. So if you do this, okay, then you know already the efficiency, the maximum attainable efficiency is 40%, which is 0.40. Okay, so if we rearrange, we have TH already given from the problem, and the efficiency, we are left with only TL. So looking at this, rearrange, you have TL is nothing but 1 minus 0.4 multiplied by TH. And TH, be careful, when we are talking about efficiency, you are your temperature, you need to use Kelvin. So this is nothing but 1200 degrees Celsius plus 273 in order to get in Kelvin. Okay. So not to be confused, actually, you have to, yeah. Okay, the whole thing multiplied by TH. Okay, so if you have this, if you solve, then you will get 883.8 Kelvin. Or if you convert back to Celsius, you have 611 degree Celsius. So that will be TL. Okay, assuming that maximum work is basically the reversible process. Okay, so that will be the second problem. Let's go to the next problem. Okay, heat pump is used to maintain a house. At 25 degrees Celsius. Okay, by extracting heat from the outside air on a day when the outside air is given as 4 degrees Celsius. Okay, so you know that the house is to be maintained at 25 degrees. Okay, by extracting heat from the already cold area, which is 4 degrees Celsius outside. Okay, the house is estimated to lose heat at the rate of 110,000 kilojoule per hour. So this is our Q loss. Okay, you know that our heat loss, this is in rate form. So Q dot loss is 110,000 kilojoule per hour. Okay, and the heat pump consume 4.75 kilowatt. Okay, remember the first statement there is to maintain the house at 25 degrees Celsius. So we want to maintain the house at 25 degrees Celsius. We know the heat loss is 110,000 kilojoule per hour. So we know that to maintain, you need to supply the QH dot to be equals to 110,000 kilowatt or kilojoule per hour. In order for the temperature to be maintained, the amount of heat transferred to the or supplied to the house should be equals to the amount of heat loss from the house. Okay, I think that should make sense. If the amount of heat transfer or supply to the house is less then the loss, you expect that the temperature of the house to drop, okay, to be getting colder and colder. And of course, if the heat supply to the house is larger than the heat loss, the temperature in the house will keep getting higher and higher. So it will become hotter and hotter. So to maintain, then the two should be exactly the same. All right. Okay, the question is this heat pump powerful enough to do the job? Okay, given the heat pump value is 4.75 kilowatt, we want to check whether this pump is sufficient enough to cater the need, which is to supply the heat to the house of that amount. Okay, given the condition of the room or house temperature 25 degrees Celsius and the outdoor temperature 4 degrees Celsius. Okay, so to do this, then if you think about it, then we can say that one way to check whether it is powerful enough is to check the ideal condition, which is for reversible process. What would be the power required to run for reversible process? Remember, reversible process is an ideal process where you don't have any what we call that irreversibilities in the system. So you would expect the power required in that case will be a lot lower. So we can compare with this. Okay. So let's look at the reversible heat pump. So COP for heat pump, reversible, you know, the relation is nothing but 1/1 minus T L/TH. Okay, that will be the equation. And you have the TL, which is 4 degrees Celsius, and TH is 25 degrees Celsius. But be careful when you use the COP and efficiency, the temperature must be in Kelvin. So plug in, you'll get TL is 4 plus 273, and TH is 25 plus 273. Okay. So if you do this, then you will get the COP for reversible process is 14.19. Okay, so coefficient of performance for reversible process is 14.19. We know in reality you will not be able to get this. Okay, this is the maximum attainable for ideal situation. So the actual situation will be lesser than this. Okay, all right. So the power required to run this reversible heat pump. This is reversible heat pump, remember? So we need to check what will be the power required to run or in order to attain this. Okay, of course, as a reversible heat pump. So again, we can also relate the COP. Okay, heat pump in general is equals to QH dot equals to divided by W. Well, actually, to be consistent, then now we use W in. Okay, simply W in dot. And this is our W in this particular problem. But we are comparing the reversible. We want to check what will be the reversible in this case. But this is the general relation. Okay, so for reversible, okay, we can rearrange. We know COP in reversible, and QH also we know that will be the amount. What will be the work required? Okay, work in for reversible, okay, is equals to QH dot over COP, the heat pump reversible. Okay, so QH is 110,000 the unit is kilojoule per hour. We need to convert that to kilowatt, which is hour to second now, 3600 second. And our COP is already calculated 14.19. Okay, so if you calculate this, then it turns out that for reversible, the power required is 2.15 kilowatt. Okay, so only 2.15 kilowatt is needed to run heat pump if the system is reversible. Of course, actual more power will be required in order to overcome the irreversibilities. So comparing with the power that we have in this problem, you can say that the work in from the problem is larger than the work in reversible. So in this case, then you can say it is powerful enough, because of course, if the power is a lot less than a reversible condition, then even the reversible process, you are not able to run, okay, to obtain. Okay, in this case, then it is more than reversible condition, which is what we want. And of course, whether it is really sufficient depending on your heat pump, the efficiency of your heat pump or the COP of your heat pump. Okay. But generally, since it is higher than power required for reversible, then it should be powerful enough. Okay, it has potential to be used for your system to cater for this amount of load. Okay, I think that should be all for this session. We will have one more session after this, okay, for this chapter.